Okay, everyone's favorite trig limits. So, as we discussed in the previous lesson, whenever you have to evaluate a limit, always start with direct substitution. Secant is a reciprocal of cosine. Cosine of pi is -1, so its reciprocal is -1 as well. Direct substitution will give us tangent of pi over 2. Sine over cosine. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. Since the tangent is undefined, the limit would not exist. Right, cotangent of -3 pi over 4. -3 pi over 4, that's a 2-quadrant rotation, but we're going in a clockwise direction, so it would land us in quadrant 3. In quadrant 3, the tangent and therefore the cotangent are positive. Reference angle of pi over 4, so reciprocal of 1 is just 1. Direct substitution here would give us sine of 0 over 0. Sine of 0 is 0 as well, so we have our indeterminate form. Doesn't mean the limit doesn't exist. We just need to look elsewhere in order to attempt to find the limit. Okay, special trig limits. Know them really well. That's my kind way of saying memorize them. You need to be able to recognize these two limits and use them whenever necessary. Now, the one thing that we will study throughout the course of the year with trig, there's never one way to solve a trig problem. Okay, so we will look at examples that highlight that. One thing to be aware of, this expression, this limit works as long as you're taking the sign of some expression and dividing by that exact same thing. So these x's sort of become arbitrary. All right, the sign of an expression divided by that same thing as x approaches 0 is equal to 1. Now this, and I'll talk about it in an example, technically those three things will be the same. All right, limit as x approaches 0 of the sine of 2x divided by 2x. Okay, so using that reasoning, I'm taking, that's not a highlighter. I'm taking the sine of 2x and I'm dividing it by 2x. Those expressions are the same thing. Now I understand that the limit statement is just as x approaches 0, but if x is approaching 0, so too would 2x approach 0. So it's not as important that this changes because we can manipulate that as necessary. Since these two expressions are the same, the limit is still 1. Limit as t approaches 0 of the sine of 3t divided by t. Okay, we obviously know which limit we're going to use. Okay, the 1 minus cosine x divided by x won't do us any good. But again, I need this expression and this expression to be equivalent. We have great properties of limit statements. All right, I can introduce a 3 because really all I'm doing is multiplying this expression by 1/3. In order to maintain balance on the expression though, I would have to multiply by the reciprocal of that out front. So if you look at what's in red, 3 divided by 3 is just equal to 1, so I haven't changed the expression at all. The 3 on the outside has to stay put, and then I'm going to multiply it by the value of the limit. And the limit of the sine of 3t divided by t would still just be 1. That's a direct application of the theorem. So the answer for that statement would be, it has a limit of 3. So here too, there's never one way to solve a trig problem. Right, two special trig limits don't involve tangent at all, but we can rewrite tangent as the sine of x divided by the cosine of x. I can't forget about my dividing by x. Dividing by x is the same as multiplying by 1 over x. It's looking a little better. Think of the two limit statements we have. I'm going to manipulate the expression to put the sine x over x, and then I'm going to multiply it by 1 over cosine of x. So we're getting a little bit better. Now, properties of limits. I can take the limit as x approaches 0 of the first expression. Now, evaluating each limit individually, this is our exact special trig limit. It has a value of 1. And then direct substitution here, cosine of 0 is 1. So our final answer, all that work, gives us the exact same value for the limit. Okay, limit as a approaches 0, sine of a divided by negative 2a. Remember this limit statement, the rule, whatever follows the trig function has to be the same as the denominator. We can't introduce numbers that follow trig functions. What we can do, however, this negative 2 in the bottom isn't affected by the limit statement at all. So I'm going to bring out a negative 1/2 divided by negative 2, multiplying by negative half. And then I'm going to rewrite my limit statement without that 2 in the denominator. So what's my answer? Negative 1/2 from the front. The value of the limit is positive 1. So negative half. It's not the same as what we did in example 2 because the 3 started as part of the trig expression. Okay, we can't introduce numbers into the trig expression. We can only introduce them out front or in the denominator. Alright, and then lastly, limit as x approaches 0 of x plus sine x, all divided by x. Looks a little different, so let's start with direct substitution. Direct substitution would give us 0 plus 0, because the sine of 0 is 0, all divided by 0. That's our indeterminate form. So let's think outside of the box. I have 2 terms in the numerator, so let's separate the numerator into 2 fractions. X over x plus sine of x over x. I'm allowed to separate a numerator as long as it gets the common denominator. So simplifying here. Alright, x divided by x gives me 1. Another useful property of limits, if I'm adding 2 functions, I can take the limit of the first and add it to the limit of the second function. The limit as x approaches 0 of any number is just that number. We know that's our special trig function. So the answer to number 5 would be 2. Okay, the squeeze theorem. In some textbooks it's referred to as the sandwich theorem. 2 assumptions have to be made. Some function f is bounded below by a function we're going to call h and above by a function we call g. We know the limit of the lower function exists, and we're going to say its limit is L. And we know the limit of the upper function exists, and it's the same limit as the lower function. If this is true, if both of these are true, then we can squeeze the limit of the middle function to be the same value as the limit of h and g. Very simple theorem, and it's helpful if we don't know what a given function is. So I have this function f of x. I don't know what it is, but I know it's bounded below by the line 2x and above by the quadratic x squared plus 1. And your question, I ask you, what would the limit as x approaches 1 be? Okay, well, using the squeeze theorem, I know that f is bounded below and above by 2 given functions. So now let's determine the limit as x approaches 1 of the line. Direct substitution gives us 2. Let me find the limit as x approaches 1 of the quadratic. Direct substitution gives us a value of 2. Since both of those limits exist and they're the same value, the squeeze theorem tells us the limit as x approaches 1 of f of x would be equal to 2 as well. And you have some homework problems that are a simple application of the squeeze theorem, like this example. Define the limit as x approaches 0. 1 over x, given this trig function bounded above by the absolute value of x and below by the opposite of the absolute value of x. All right, now just to recall, absolute value of x, that's our v. So the opposite of that would just be the reflection. So this trig function is bounded by above by the absolute value of x and below by its reflection. If we want to find the limit of x approaches 0 of the trig function, direct substitution would give us 0 times the sine of something that's undefined. So direct substitution doesn't do us any good. So by the squeeze theorem, direct substitution, the limit as x approaches 0 of negative absolute value of x would just be 0. Limit as x approaches 0 of positive absolute value of x is 0. Therefore, limit as x approaches 0 of the function in question would be forced to be 0 as well. Okay, that's it for now.